For those of you who were not here today, we're contrasting series with parallel circuits. First thing you may need to do is just pause and write all this stuff down. But when we're comparing a series to a parallel circuit, what we find is that they have some remarkable differences. In a series circuit, all the resistors are in one continuous loop. So I have a resistor, I have another resistor, I have another resistor, and then I have to have a power supply. In this case, we're going to put in a battery as our power supply, and it comes back. So we have a complete loop. It goes through all three resistors. There's only one possible pathway to go through all these three resistors. So that's in series. Over here in parallel, the resistors are on separate branches. So I'm going to draw my battery over here, and what happens is I have a resistor here, or I have another resistor over here, or I have another resistor over here. And so realistically here, I have three different pathways that this can happen. I can come from my power source, I can go through that resistor and come back, or I can come from my power source, go through this resistor and come back, or I can do that with the third one. So I have three different pathways that can happen here. So they're on separate loops, separate pathways. Now what we find is that the voltage drop over here on the series side, the voltage drop is going to be proportional to the resistor size. So if this is like a 10 ohm resistor and this one is 20 ohms and this one is 30 ohms, then clearly the 30 ohm resistor is stronger, 3 times stronger than the 10 ohm resistor, and so it's going to take 3 times more voltage to go through that one. The voltage drop explains how much voltage gets used up going through there. So if I have a certain amount of voltage going before that resistor, how much did it drop by the time I get to the other side? That's where the phrase voltage drop comes from. And it's basically how much voltage do I use up. Now going around the circuit, we will always use 100% of the voltage. So by the time we get back to the battery, we have used all of the voltage. But again, it's going to be a proportional mix of what happens to what. How that actually calculates out, we learn when we learn about series circuits and how to calculate those, which is another video. But right now we just know the voltage drop is going to be proportional here. Now on the parallel circuit, the voltage drop is going to be equal everywhere. Because if I start at my battery and I go around the circuit and I get back to the battery, I went through just one resistor and got back to the battery. And again, I have to use up 100% of my voltage. So that means I lost 100% here, I lost 100% going through here, I lost 100% when I went through here. So in all of these, the voltage drop is always going to equal whatever the total voltage was, that's going to equal what the voltage drop in that segment is. As far as current goes, in series, since there is only one pathway all the way around the circuit, there is only one possible pathway to go, there's no way that I can pull more current through the 10 than I do through the 20 and through the 30 because there's only one branch. If you think of it kind of like water, if water's flowing through that pipe, since there's only one pipe, all the water has to go that went through the 10 has to go through the 20, has to go through the 30, except we're not talking about water, we're talking about charge. So any charge that we're shoving through this is going to work that way. So the current is going to be the same everywhere over here. But over here in parallel, the current is going to be inversely proportional to the resistor size. So again, if I have a 10, well, let me just redraw this because it's getting messy. So if I have my battery, that's a beautiful battery. If I have my battery here and I have resistor, say again, we have that one's a 10 and this one's a 20 and this one's a 30. Well, what happens here is the current through a smaller resistor, if we have less resistance, we have more current. And so this one is going to have a lot of current going through here. We're going to have less current going through here. How much less? Again, it's inversely proportional. So the little one, if 10 is 1/3 of 30, then it's going to have 3 times more. That's inversely proportional. You look at that ratio there. So we're going to have 3 times more current going through here than we do going through this one. The 20 would have twice as much as the 10, or 1/2 as much as the 10, excuse me, because it's inversely proportional. So the current's going to be less in the big resistor, more in the small resistor. That's pretty common sense. That should be pretty easy. Going to switching. In a series circuit, since there's only one possible pathway, anywhere I interrupt this pathway it's going to interrupt the pathway for everything, which means it's all off or all on. They're either all on or they're all off. You can't have part of them on and the other part off. It doesn't work that way in series. This is like cheap Christmas tree lights. If you have cheap Christmas tree lights, one bulb goes off, the whole string goes off, you have no idea which one is bad, but you know one of them is bad because they all went off. On the other hand, if you have good Christmas tree lights, they are in parallel, and one goes out and you go, oh, that one went out. So say the 20 goes out. If the 20 goes out, do I still have other pathways that I can make it? Sure. I can still go through the 10, I can still go through the 30, so I still have two different branches I can do, which means they're not all going to be all on or all off. So I have multiple switching options over here. I can put a switch just on this branch and just kill the 10. I could put a switch right here and just kill the 20. I could put a switch anywhere in here and just kill the 30. If I put a switch here or here, that would kill everything toward the end, both the 20 and the 30. If I put a switch here or here, it would shut everything off. So there's multiple spots where I can stick a switch and have a different result. In parallel, in series, no matter where I put a switch, they're all on or they're all off. That's all there is to it. Now, as far as power goes, power consumption is dealing with, of course, we know that P equals IV. So if P equals IV, if I have to shove through 3 resistors to get back to the battery like we're doing here in series, if I'm shoving through all 3 resistors to get back, then that means I'm shoving through more, which means my current's going to be lower. If the current is lower, then the power is lower. So this is going to be lower power. Over here in parallel, again, since I'm pushing through them individually, the current in each branch is going to be higher, and if the current is higher, then my power is higher. So over here, parallel will always be more powerful than series if we're using the same things. So like if I have 3 light bulbs in series and identical 3 light bulbs in parallel, the 3 light bulbs in parallel will be very bright. In series, they'll be dim. The bright ones are using much, much more power than the dim ones are. The last part, number 5, more resistors is more resistance. So if I add an extra resistor here or another 2 resistors here, what's going to happen is now I have to push through more things. If I push through more things, then obviously the overall resistance is going to go up, which means the current is going to go down. That's pretty straightforward. Nobody has trouble with the series circuit part. In parallel, though, if I add an extra circuit over here and an extra resistor over here, if I'm adding extra branches, you're saying, hey, more resistors is less resistance? Yes. And it sounds a little weird until you stop and think about lines. If I'm going through a line, like in series, if I have a setup like here where I have to go through one table and answer these questions, and then I go to the next one, and then I go to the next one, if you add a couple more stops in this, it's going to slow everything down. That's the same way it works in series. But the parallel is more like checking out at the grocery store. If you're checking out at the grocery store, what happens is every time you open another lane in the checkout lane, now there are more possible pathways for me to get through this line. I'm not going to go through all of these lines, I'm just going to go through one of them. And the more options I have, the easier it's going to be for me to go. So in this case, in this analogy, the resistance would be the amount of time it takes me to get out the door. If I only have one checkout lane, then it's going to take forever to get out the door when a bunch of us are there. But the more checkout lanes that are open, the faster we're all going to get through and out the door. That doesn't mean each checker is going to check out the same. So like the 10 ohm checker is different than the 30 ohm checker. And so the 30 ohm checker is the new guy. He's a little bit slow, and so the resistance is higher there. He's not going to get as many people to flow through there. The 10 ohm checker is the experienced one. They're whipping people through the door. No problem. They know what they're doing, and so the resistance there is a little lower. The current is higher. You have more people flowing through his station. But as we add resistors, no matter what they good, no matter how good or bad they are, every time we add resistors at the end, there are more options available, so the overall resistance goes down. And that's pretty much the basic differences between series and parallel. If you understand these basics, it's a whole lot easier once we get to doing the problem type things. So that's it.